So this is the answer key walkthrough for the practice quiz on balancing and classifying chemical reactions. So on each page, there's an equation, which you need to identify the type of reaction that's shown in the equation and then balance the chemical equation. So let's take a look. So the reaction type, well, you can do this a couple of ways. A lot of times you can use process of elimination, at least to narrow down the possibilities. And then there are always key features to look for to identify specific types of reactions. So I'll sort of show you both ways. In this case, the key thing I'm looking at is the fact that this reaction includes oxygen as a reactant. So O2 is shown on the left-hand side of the arrow. That is almost always going to be a combustion reaction. Now, let's take a look at the other possibilities and see if we can eliminate them. The first type of reaction is synthesis. A synthesis reaction must have one product, only one substance on the right side of the arrow. This particular reaction has two, so we can immediately cross off synthesis as a possibility. On the other side, decomposition has one reactant, so one thing on the left side of the arrow. Again, this equation shows two things on the left, so two things on each side means it can't be synthesis or decomposition. We can cross those off right away. So the other two types of reactions are single and double replacement. Now, a single replacement reaction has one element and one compound on the left. This does have that. It's got a compound and an element. But for it to be a single replacement reaction, it must also have one element and one compound on the right. This particular reaction has two compounds on the right. Can't be single replacement. And then double replacement has to have two compounds on both sides, or two compounds on each side. Since this one has the element as a reactant, that rules out double replacement. So process of elimination gets us to the same result. The only reaction that it could be is combustion. Now let's take a look at balancing the equation. And we've actually looked at, I think, this exact example before in class and even in some homework. So let's take a look at it, though. It should be a good practice. First thing I always like to do is split the reaction down the middle where the arrow shows. Count up the atoms on both sides. See, there are 3 carbon, there are 8 hydrogen, there are 2 oxygen. The counting here is pretty straightforward because each element only appears once. Each element has a subscript that we can see. Just write down those numbers and you're done with the counting on that side. On the other side, we have carbon in the CO2 molecule. There's no subscript, which means there's 1 carbon. Just to do it in the same order, hydrogen next. Over here on H2O, there's 2 hydrogens. Oxygen in this case is a little bit trickier because it appears twice in the CO2 and the H2O. I like to keep the elements together as much as possible rather than counting 2 different cases of oxygen. You could do that. There's nothing wrong with that. I just like to keep things condensed a little bit. So in this case, there's CO2 plus H2O. Altogether, there are 3 oxygens. Now, where to start? Just going to start at the beginning and go from there. Carbon is 3 on the left, 1 on the right. I can't make the 3 on the left any smaller because the subscript I can't change. So I'm going to start by seeing if I can make the right side match the left side. In order to do that, I have to take the 1 and multiply times 3. Remember, when you add these coefficients, you are multiplying, you're not adding. That gets confused sometimes, and sometimes it actually looks like it works when you're adding, but you're really multiplying. So carbon is now 3 on both sides. However, the 3 coefficient here affects everything that's in that compound. So I've also multiplied the oxygen. 3 times 2 is 6, and I still have 1 over here, so that's 7 oxygen. All right, now I'm going to work on the hydrogen next. Hydrogen is 8 on the left and 2 on the right. Can't make that 8 any smaller. And I have the 2 on the right, which means everything I do is going to be a multiple of 2. Well, conveniently, 8 is a multiple of 2. So if I put a 4 in front of the H2O, it multiplies the H2 times 4, which gives me 8. It also, again, affects the oxygen. We said there were 6 here. Now there's 4 more here, 4 times H2O. That gives me a total of 10 oxygen. So the carbon is balanced, the hydrogen is balanced, the oxygen is 2 on the left and 10 on the right. So now I have more on the right than the left for the first time. So I'm going to have to go back over to the left-hand side. I've got O2, and I want O to be 10. So I'm going to multiply that one by 5 rather. That gives me 10 oxygens. All the elements are now balanced, and I am done with this equation. All right, next one, reaction type. So this has a compound and an element on the left, and an element and a compound on the right. So this has the form so AB plus C, and then this would be B plus AC. So really what's happened here is the B and the C have traded places. When you have an element and a compound on each side, and one of those elements has traded places, that is called a single replacement. Okay, because one element has been replaced in one compound. So element, compound, that means single replacement. Right, now let's balance it. We'll start by counting up the atoms on both sides, and then we use the coefficients to even things out as needed. And I'm going to put the line down the middle to separate everything, and then I'll start matching up elements using coefficients. Okay, on the left I have H2, I have S1, and then I have Cl2. On the right I have 1H here, I have 8 sulfurs, S8, and I have 1 chlorine. Okay, so I'm going to start by fixing the sulfur. And I'm going to fix the sulfur by seeing that there's 1 on the left and 8 on the right. And so I have to multiply H2S times 8 to make this 8. Now, why did I pick that and not start with the hydrogen? Well, because I could see that I was going to have to do something to the sulfur. And so if I started by fixing the hydrogen, I could kind of tell that I would probably have to go back and do something else to it because of the sulfur. So I wanted to start with the bigger change. That's why I picked that and not just starting at the beginning. So because it's 8 times H2S, that now means I have 16 hydrogen on the left and 8 sulfur. So I fixed the sulfur. All right, now let's take a look at the hydrogen. Now that I've made a big difference in the hydrogen, I'm going to go over here. I'm going to make this 16. So that makes 16 hydrogen. Now I've got the hydrogen balanced. But now I've got the chlorine, because this is also now 16. The chlorine is out of whack. So 16 on the right, Cl2 on the left. Again, it's going to be a multiple of 2. 16 is already a multiple of 2. So I'm going to mark that as 8, or put a coefficient of 8, which now gives me 16 chlorines on both sides. I had said at one point, be wary if your coefficients start getting into double digits. It does happen. So it doesn't mean you're wrong, but sometimes you need to take a look and say, well, could I reduce those down or simplify my ratios? In this case, I can't, because I actually still have a 1 here. So there's nothing simpler than 1 without decimals or fractions. So even though these are big numbers, the 8, 8, 16, especially since I have the 1, I can't simplify, I can't divide by 2, because then I end up with a half, and I can't have that. So let's move on. Okay, reaction type. 1 reactant, 2 products. So I have a complex substance breaking down into simpler substances. That is always, always, always decomposition. Okay, so the format here is AB breaks down into A plus B. Okay, anything like that where you have a single reactant and multiple products, decomposition is going to be your choice. Now, to balance it, count up the atoms. I have nitrogen, hydrogen. On the right side, I have N2, which means 2 nitrogens, and H2. This should be a 2. I fixed this in the class kick, so hopefully you could see that. If not, I apologize. I made a mistake on that, but we're gonna do it right. So I have H3 and H2. Why start there? I could start with a nitrogen, but again, I'm looking at the 3 and the 2, and I know that I'm gonna have to do something to get those to be equal. So I'm starting there because I'm worried that if I start with the nitrogen, I know I'm gonna have to change the hydrogen, and that might mean going around another step. So since I know I have a 3, which is a subscript, can't change the 3, a 2, which is a subscript, can't change the 2, in order to get those to be the same, I have to find a common multiple. In this case, the common multiple is going to be 6. So if I do 2, that gives me 6. And if I do 3 over here, that gives me 6. Now the 2 on the left-hand side, there's only one substance. So the 2 I put there also affects the nitrogen, which gives me a 2. And I already have N2 on the right. So I actually balanced it by putting those 2 coefficients in to fix the hydrogen. And at the same time, conveniently, I fixed the nitrogen. Now you could say, well, if I had put the 2 there to do the nitrogen first, that would have given me the 6, and then I would have fixed the hydrogen. That's true. And if you chose to do it that way, you absolutely can still get the right answer. But again, just trying to give you an insight into the thought process of, where should I start? Is there something that's a clear change that I'm going to have to make? And will that affect other stuff later on if I don't do it first? So that's kind of the things I look out for. Next reaction. Okay, reaction type. I got all sorts of stuff here. I've got compounds on both sides, 2 compounds on each side. So I'm going to call this AB, and I'm going to call this CD. And then on this side, I have AD and CB. So the back halves of these have traded places. The D and the B have switched. The other thing is the only reaction type of the 5 that we've talked about that has 2 compounds on both sides is double replacement. So even if you're not sure about, well, which halves were switched and things like that, if you have 2 compounds on each side, you're very safe calling it double replacement and not worrying too much about it. So there we go. We've got that done. Now let's balance things. Again, looking for things or kind of explaining how I do these and things to look out for that I find help make things easier for me. When you have these groups of atoms, like you see the parentheses, especially, anytime you see parentheses, keep an eye out for groups of atoms that look the same on both sides. So in this case, I'll start with calcium just because it's first in line. There's 1 calcium on that side. Over here, there's also 1 calcium. So with any luck, I'm not going to have to do anything that changes the calcium because they're already balanced. Now the next thing is the NO3. Again, anytime I see parentheses around something, I'm going to immediately look on the other side and see if that same group of atoms appears on the other side. In this case, it does. Here's NO3 over here with all those elements together. So since it appears as the same grouping on both sides, I'm going to treat that as one thing. And I'm going to say that on this side, there's 2 groups of NO3. On this side, with no parentheses and no extra subscript, there's 1 group of NO3. Then I'm going to look at Na. There's 1 on that side, 1 on the right. And again, here I've got OH. And over here, I have OH in parentheses. Always looking for those parentheses. So since I have an OH group here and OH in parentheses over here, I'm going to treat that as one unit. There's one OH group on the left. Because of the parentheses, there's two OH groups on the right. All right, now let's balance. Calcium, again, I'm not going to touch that if I don't have to because it's already balanced. NO3, I've got two on the left and one on the right. The subscript on the left means I can't make that smaller. So I'm going to have to put a coefficient over here of at least 2. Putting a coefficient of 2 there gives me two NO3 groups because it's NO3 twice. It also affects that sodium, which makes that a 2. Okay, so now the calcium is balanced. I haven't done anything with that. The sodium, the NO3 is balanced. The sodium is unbalanced now. It was balanced to begin with, but because I had to change the NO3, I had to also change the sodium. Well, go back over to the other side, put a 2 in there to make it balance out with the sodium on the right. That gives me two NAs. It also doubles this, so I have two OHs, which works out well because I had two OHs on the right. So with just those couple of changes, I've balanced everything. Okay, so again, the tip here, the thing to look for is when you see parentheses, immediately look to see if that same grouping appears on the other side. And it could be left or right where the parentheses are, it doesn't matter. But parentheses trigger me to say, okay, OH is in parentheses on the right. Is it an OH on the left? Yes, it is. So I'm going to treat those as one group. Could you also break them up and just count the individual elements separately? Of course. And you can absolutely do that and come to the right answer. For me, though, that takes a little bit more counting and a little bit more tracking. I'm always looking for tricks that make it a little more efficient. Next one, reaction type. I was just talking about the fact that the only type of equation that has two compounds on each side is double replacement. And that's what we have here. So yes, there will be cases where you might have the same reaction type more than once. Okay, don't eliminate something from your mind because you've already used it. There might be 3 synthesis questions on the quiz. So the fact that you used it doesn't mean you can't use it again. It is the right answer is the right answer no matter how many times you've used it before. All right, now the balancing. Hg is 1 on the left because there's no subscript. Hg over here is 3 because it's got a 3 subscript. Hey, parentheses, does that mean that there's groupings on the left and right? Well, here's an OH group on the left, and there is not a specific OH group on the right. The OH group is really part of the H2O, but I'm not gonna try to keep track of it that way. I'm just gonna say, all right, OH is oxygen and hydrogen. There's no subscripts in the parentheses. There's a 2 on the outside, so that means these are each going to be 2. And then I've got another thing with parentheses, which is the PO4. That one does appear on both sides, so I'm going to keep that together. On the left-hand side, there's one group of PO4. On the right-hand side, oops, sorry, let me finish the counting over here. So H2O means 1 oxygen and 2 hydrogens. And then PO4, on this side, there's 2 of them because there's parentheses with a subscript. All right, and you might say, well, wait a minute, you didn't count those oxygens when you wrote the oxygen here. Again, because I'm keeping this group together, I'm not going to count it twice. So I'm counting it as part of the PO4, not part of the oxygen on its own. So again, if that gets really too confusing for you, just count all the elements separately and you can still get the right answer that way. All right, so the first thing I'm going to look at is, well, I'm going to have to multiply the mercury, the Hg, and then I've also got the PO4, which has to be changed, and the oxygen and hydrogen I'm not too sure about. So I'm going to start with the hydrogen, the mercury, the Hg, and see where that gets me. So if I've got 3 on the right and 1 on the left, that means I need to make this a 3. That gives me 3 mercuries on both sides. And then the 3 multiplied by the little 2 means now I have 6 oxygen and 6 hydrogen on this side. Oh, I messed that up. I actually originally had, I was too busy talking about the OH being different, and I forgot to count this H3. So hopefully I didn't leave that for too long where you're wondering why you got it wrong. You didn't get it wrong if you said that there were originally 5, because there are. 2 in the parentheses and then 3 over here with the H3PO4. All right, now back to where we were. Hg, so 3 times HgOH2. So 3 times 2 is 6, plus 3 more, that's 9. Okay, so there's 6 in here now, and there's 3 here, so that gives me the total of 9. The O in OH, 3 times 2 is 6, and that one I'm not counting this over here because I'm keeping that as part of the PO4 group. So sorry, I caught myself there. All right, now the PO4s. Well, there's 2 on the right and 1 on the left. Well, the simplest fix for that is to put a 2 in front of this one over here. That gives me 2 PO4s. It also changes the number of hydrogens again. So originally I had 5. Then I multiplied this grouping over here by 3, which gives me 3 times 2, or 6 hydrogens in that substance. 2 times 3 gives me 6 here. Now I've got 12 hydrogens. So I'm changing that one more than once, which sometimes you'll have to do. All right, so now I've got the mercury balanced. I've got the PO4 groups balanced. That leaves me with hydrogen and oxygen, which looks really like it's way far off, but 6 and 12, that's a 2-to-1 ratio. Well, H2O has a 2-to-1 ratio. So when I want to get the oxygen to 6, I put a 6 in front of H2O. That gives me 6 oxygen. 6 times H2 gives me 12 hydrogen. So sometimes, when you fix one, you fix the other one at the same time. So don't worry if you are fixing something and it looks like you kind of broke something else, because a lot of times these things work out as you go through the process, and they can all be balanced. So even if it looks like it's not going to work, you got to just go forward and do the simplest things first, and then work your way through whatever else needs to be changed. Okay, here we go. What reaction type is this? Well, this has 2 elements on the left, 1 substance on the right. The elements have combined, which is called a synthesis reaction. It's also called a combination. So you can call it either one, and I would be fine with either answer. Okay, so that's that one. It's the only one that has 1 substance as a product. Synthesis. Sometimes combustion reactions can have 1 product, but then they're also synthesis reactions. This one isn't combustion because there's no oxygen as a reactant. All right, count them up. Silicon, 1. Sulfur, 8. On the right, silicon, 2. Sulfur, 4. Well, I'm going to have to multiply the silicon on the right to make it equal to silicon on the left. So again, you might look at it and say, well, shouldn't I just start with the silicon? You could, and you could have get the right answer. But the difference, the thing I know I'm gonna have to change this substance because I have to fix this sulfur. So I'm gonna start with that. 8 on the left, 4 on the right, multiply it by 2, that gives me 8 sulfurs. It also means 2 times this, which gives me 4. Got a little messy, sorry about that. All right, gives me 4 silicon. Now I've got 8 sulfurs on both sides. I've got 1 silicon on the left and 4 on the right. So if I multiply that by 4, it gives me 4. Again, could you have gotten the right answer if you started with the silicon and say, oh, I need to multiply that by 2? Yes. it just would have meant you had to kind of go back around, because you would have done the 2, and then you would have had to fix the sulfur, which required you to put the 2, and then you would have had to go back and change the 2 to a 4 on the silicon. Can be done, makes a little extra work, but if that's how you did it, you could have still gotten the right answer, and the numbers are what the numbers are no matter how you get there. All right, last one on these, and then a couple of other questions. Type of reaction. I've got element, compound, compound, element. So the order in which these things appear is not what's important, it's what they actually are. Element, compound on both sides. That is a single replacement. Yes, we had one of those before. But we also have it now. Okay, so again, you could have the same type of reaction more than once. Don't rule it out just because you've already used it. All right, now balance this thing. Count them up. Aluminum, iron, chlorine. Aluminum is a 1, iron is a 1, chlorine is a 2. Over here, aluminum is a 1, iron is a 1, chlorine is a 3. Well, if it wasn't for that chlorine, we'd already be balanced, but it is what it is. So again, I've got a 2 and a 3, which are both subscripts. So I cannot change those numbers. I have to find the common multiple. Again, 2 and 3, the common multiple is 6. So multiply this by 3, multiply this by 2. 3 times Cl2 gives me 6. It also impacts this iron, which makes it a 3. The 2 times Cl3 over here gives me 6. Also affects the aluminum. In fixing the chlorine, I broke everything else. So aluminum is going to be times 2, and iron is going to be times 3. All right, so 2, 3, 2, 3. So you can't reduce that and make it any simpler, and all the numbers are now balanced on both sides. So there you go. That is the answer to that one. The last couple of questions are a little bit more open response, a sentence or two. How is decomposition different from synthesis? You can explain this however you want. Decomposition involves a complex substance breaking down into simpler substances, whereas synthesis is simpler substances becoming more complex substances. Okay, or you can say decomposition is a single substance breaking down into smaller components, and synthesis is smaller components combining to form bigger components and substances. So however you want to put that in your own words, that's fine. Again, the question on the test will be slightly different, but it will be asking you to explain some aspect of these different types. It might be the difference between single and double replacement, or what is required in a combustion reaction, which I actually think is another question on here. Let's take a look. Yep, here we go. What does a combustion reaction require, and what two products are typically generated? The second half of that is a little bit tricky, but I'll explain. What is always required, though, is an absolute. For our purposes, a combustion reaction must always have O2 as a reactant. Okay, that is the defining feature of a combustion reaction. O2, the element, is a reactant on the left side of the equation. If that happens, call it combustion every time, and you will be right every time. The second half is what are typically generated. And the answer that we're looking for here is CO2 and H2O. And I think this was mentioned in one of the videos you watched, and it was worded, I think, a little bit incorrectly or a little incompletely, I guess. This is true anytime you burn a hydrocarbon like propane, because it's carbon, hydrogen, and oxygen. That's the reaction. The products of those types of reactions is almost always CO2 and H2O. So when they say you always have that as a product, you always have that when you burn a hydrocarbon, yes. But there are other combustion reactions that don't involve carbon and hydrogen at all. So if you don't have carbon and hydrogen, you can't have CO2 and H2O. So again, the answer this was looking for is CO2 and H2O. But if you struggled with that, don't worry, I'm not going to ask you that specific question on the quiz. I might ask you something else about combustion, like what other type of reaction is combustion sometimes the same as, which would be synthesis. I could ask you something like that. And then how does a balanced equation demonstrate the law of conservation of mass? And I'm not going to write this all out. But the law of conservation of mass says that atoms are not created or destroyed during a chemical reaction. They're just rearranged. So in order to show that, the chemical equation has to show the same number of atoms on both sides of each element. So we balance the equation to follow the law of conservation of mass, because if we have different numbers of atoms on either side of the arrow, then that doesn't follow the law of conservation of mass, and we have to obey because it's the law. So again, the three questions that we just went over, there will be different questions specifically on the quiz, but they will be those types of concepts. Understanding how to compare and contrast the different types of reactions and what makes them unique. And then specific things about, why do we balance an equation? I'm not going to ask you things like how many different types of reactions there are, because depending on who you ask, there's 4 or 5. But things like that to keep an eye on. So be able to balance the equations, classify the different types of reactions, and then answer questions comparing and contrasting the different elements of the different parts of these equations.